In this video, I will show you an example, one application of Ampere's law. So I have here a current, a conventional current that flows in the z direction. So let's say that this is the current the magnitude, and it points in the z hat direction. And I know from the right hand rule actually that this current will create a magnetic field that is curling around the wire, and B will point in the counterclockwise direction. Now I can write B as the magnitude of B times the phi hat direction. And here I am using the cylindrical coordinate system. Now, so I have the direction of B, and I can also write dl. Now in cylindrical coordinates, the vector dl will be ds s hat phi hat now using here is equation 1, this is equation 2. I'm gonna use equations 1 and 2 to find b dot dl. And I know that phi hat dot with s hat will be 0 in the same way that phi hat with z hat will be 0. So the only term that will survive is the phi components. So I have b s d phi and then phi hat dot with phi hat, but I know that this is just 1. Now I have chosen the counterclockwise to be the direction of integration. So my dl will have to be curling in the same way that B is. And when you do that, you will need to make sure that B dot dl will give you a positive number. Okay, because I'm integrating, the path that I'm following is counterclockwise. Let's say it has a radius s, and also I'm integrating counterclockwise. So I am using the result of the integral of the dot product, and I'm integrating from 0 to 2 pi, and this will give me 2 pi s times the magnitude of B. Now this is the left side of Ampere's law. Now I have, according to this, the direction of integration counterclockwise, a positive current will need to be moving out of the page. And this is what I have from the problem. I do have a current that is flowing in the direction that points in the positive z hat direction out of the page. So the current enclosed is just mu naught times I, and then combining, let's call this one equation 3, combining the left side with the right side and using Ampere's law, I get and from here we can solve for B as mu naught times I over 2 pi s. Now remember, this is gonna give me the magnitude of B. If you want to include, to write B as a vector, remember from equation 1 I had written B as the magnitude times phi hat. You will have to write what you found, mu naught times I over 2 pi s times phi hat. Okay, this expression will give you the vector for the magnetic field.